One of the best features of VAR and VECM models is their ability to forecast the future. These models rely on the lags or previous period information to explain the current behavior of variables. This also means that to predict the future, we only need information on the current values of the variables. For example, variables in time t depend on the values of variables in time t-1. Similarly, to forecast their values in the t+1 period, we only need the information on the variables in time t. In our example, we have 55 observations on 4 variables and the underlying VAR model has 2 lags. This means that to forecast the next time period or the 56th value, we only need information on past 2 lags. We already have that information from the 55th and 54th observations. To predict further in the future, we can simply use the previously forecasted values. For instance, to forecast the second period in the future or the 57th value, we can use the 55th observation and the forecasted values of the previous period of 56. These dynamic forecasts allow us to predict future values for as many time periods as we want. However, we must keep in mind that the longer the forecast horizon, the more inaccurate the forecasts will get. Stata and IR provide functions to easily calculate forecasts after VECM estimation. The fcast compute function in Stata and the predict function in IR can be used to get dynamic forecasts from VECM. The option step in Stata and n.ahead in IR can be used to specify the number of periods in the future that we wish to forecast. In our example, we have specified 4 here. Since we have quarterly data, this means that we are forecasting 1 year into the future. In the Stata command shown here, forecast is simply the prefix we are assigning to the forecast names. After obtaining the forecasts, we can just as easily plot them. The fcast graph command in Stata and the generic plot function in IR can be used for this purpose. These will automatically plot the confidence intervals along with the forecasts as well. Let us take a look at the plots. The first part shows the original data of 55 observations here. The forecasts are shown in the dotted blue line and the confidence bounds are in the dotted red line. These forecasts can also tell us about the performance of the VECM model in reality if we have a test set. Suppose, if we had the actual data for these 4 periods or if we had kept some observations aside for testing, we can compare the forecasts to real values and judge the forecasting performance of the model. Impulse response functions or IRFs show the effects of a shock or impulse over time on the variables in the VECM. By default, most software packages consider a 1-unit shock to a variable and then calculate the effect of that shock on all the variables in VECM model. Suppose there is a positive shock to IBO variable. This shock is delivered through the error term of the IBO equation, which is the third equation of the VECM. This positive shock will increase the value of IBO. In turn, this shock will also affect LRM, LRY, and IDE over time. The impulse response functions let us examine these effects by showing the response of all variables to a shock. The function IRF in R and the function IRF create in Stata lets us estimate the impulse response functions. We can also choose the variables where we deliver a shock called an impulse, and we can also choose the response variable. Here, we have decided to deliver a shock to the IBO variable. Response is equal to LRM means that we want to see the effects of the shock to IBO on the variable LRM. Using n.ahead and step, we can specify the number of time periods that we want to consider. n.ahead or step is equal to 16 means that we will see the response of LRM over 16 time periods after the shock is delivered to IBO. We can choose to estimate IRFs, orthogonalized IRFs or OIRFs, and cumulative IRFs if we want. OIRFs allow us to include contemporaneous effects, that is, we can allow shocks to affect some variables in the same time period as the shock is delivered. Here, we will estimate simple IRFs without any contemporaneous effects. Let us illustrate how the IRFs are interpreted using an example. Remember that we discussed the behavior of LRM and IBO variables in Tutorial 7. We talked about how LRM is a follower and IBO is a leader variable in our example. This means that any attempt to increase LRM or demand for money by delivering a shock to LRM directly will not work because it will simply converge back to its equilibrium value. The increase in LRM will only be temporary. We can see this in the plot of IRF as well. In the plot, we can see that a 1-unit shock to LRM will initially increase LRM by 1 unit. This also makes sense because the shock is delivered directly to LRM. However, the effects of the shock will only last for a few time periods because the IRF is converging back to 0. If we look at the confidence intervals, the lower bound touches 0 after about 4 time periods. This means that the effects of the shock might even die out in 4 periods or 1 year since we are dealing with quarterly data. Even though the confidence bounds are huge, we can expect the effects of a shock to become 0 in about 2 years. These types of shocks are known as transitory shocks in VECM because they affect the response variable temporarily. The IRF will eventually revert back because the effects of the shock die out. Now, let us see whether we can change the demand for money or LRM through IBO. Earlier, we discussed that IBO is a leading variable and it will not converge back to equilibrium because its adjustment parameter is insignificant. We can see something similar in IRFs by giving a shock or impulse to IBO and observing its behavior over time. In the plot here, we can say that a positive shock to IBO will permanently increase IBO because the effects of the shock are not reverting back to 0. Moreover, the confidence bounds are well above 0 as well. This shows that IBO may not converge to equilibrium after a shock. This is exactly what we expected. Now, let us see how a shock to IBO will affect LRM or demand for money. The plot here shows that a positive shock to IBO will decrease LRM. We expected this because IBO and LRM are negatively related. Moreover, we can see here that the change in LRM will be permanent because the IRF is not reverting to 0. The confidence bounds are well away from 0 as well. This further confirms our expectations that we can change LRM by delivering a shock to IBO. In order to permanently increase LRM, all we need to do is deliver a negative shock to IBO. That is, we can decrease IBO to permanently increase the demand for money. These types of shocks are known as permanent shocks in VECM because the IRFs do not revert back. In the IRFs shown in this video, we can see that a VECM can have 2 types of impulses or shocks. First, we saw a transitory shock in LRM due to a shock to LRM. Second, we observed permanent shocks to IBO and LRM due to a shock to IBO. This is different from the VAR models because they can have only transitory shocks. This is because VAR models are applied to stationary variables, so their IRFs revert to 0. Therefore, impulse response functions are one of the most useful applications of VECM as they can help understand the behavior of variables and their relationships. They can be especially useful in policy analysis. Thank you for watching, and I hope you like this series of tutorials. Please feel free to contact if you have any doubts or questions.